Okay, so let's talk about domain and range. We're still talking about functions. So the picture just goes like this. So it's just this is also, it's just as long as there's just one output for the input, so the input is not allowed it's not allowed to go two different, it's only allowed to go, the function is only allowed to send it to one thing, but two different inputs could have the same output. So for example, 1 and -1 could go to the same place. 2 and -2 could go to the same place. Here's the number 0. 0 could go to 0. So this is kind of in abstract, in sort of the abstract, it's just the set of inputs. So it's the set of all valid inputs. So the set of all valid inputs, and then the range. So the domain of f, and then the range of f. We have a particular function in mind. Let's say, in this case, I'm giving you f of x is equal to x squared. The set of all outputs. So notice that something interesting is going on here. We're not getting any, we can plug in any number we want. We can always take a real number and square it. The domain is all real numbers, which is, maybe it's been a while since you've seen interval notation, but a real number there's this placeholder called -infinity that just says that every real number is bigger than -infinity. So we can always write down an interval, and then just the left endpoint is this hypothetical -infinity. Nobody ever actually gets to -infinity, but you can keep going that way as long as you want. And then at the other opposite extreme, every real number is less than, strictly less than positive infinity. And with the range, well, the easiest way to see this is with a graph. And that is, well, you put the inputs on the horizontal axis, and so you just graph that relationship. You take just your inputs and your outputs, and what happens is every time you plug in a real number, it's either positive times positive, which is positive, or it's negative times negative, which is again positive, or you can get 0 times 0, which is 0, is the only other thing that can happen. 1, 2, 3, -1, -2, -3. For y equal x is equal to x squared, this one is very famous. Let's just do a table here. X, y, we do 0. 0 times 0 is 0. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and let's put the word graph down here. -1, -2, -3. So -1 times a -1 is +1, -2 times -2, that's double negative, -3 squared is again double negative, which is 9. So we go 1, 2, 3, 4, 5, 6, 7, 8. I'm trying to keep it equally spaced as much as I can. That's a little bit better. So here's the y-axis. So 1, 2, 3, 4, 5, 6, 7, 8, and oh no, there's 9 up there. Okay. So 1, the y is 1 and 2. The y value is x is 2, y is 4, x is 3, y is way up here at 9. So if you really wanted to get a really good graph of this, well, maybe you would sample lots and lots of points, and then I know you're very busy, and if there's like 30 problems, you know, maybe 5 or 6 points is all that you really need to graph. You just have to make sure you capture that point right there at 0 seems to be really important. It's like everything else is sort of symmetric after that. But the domain, let's bring back the colors. Let's use the blue. Well, you could, so the domain is the inputs. Well, how many inputs are there? Well, you can have any input you want in the entire real number line. That's no problem. Let's take a picture of the range here. So you can, let's see. Well, remember, where does it start? Square brackets means that the int point is actually included. Open parentheses means that it's not included. Customary to use open parentheses because -infinity is an abstract idea. It's not an actual number. It's not actually a number that's included in the set. But every real number is bigger than this idea of -infinity, so we use open parentheses to say everything bigger than -infinity and less than +infinity. But for the range, we start at 0 is actually okay, but we can never get negative numbers. So we actually include 0. The textbook kind of does something like this. They would go like this. They would draw an interval and then, well, what happens? Well, when x is 0, the output is y is equal to 0, and then we pick x as they go farther out to the right. It looks like the y's keep going and going, and we can get basically anything. But we include 0, and we keep going and going and going all the way out to, but not including +infinity, because you plug in a number, you get a number. You don't plug it. You never get the actual. You never actually get to infinity. It's just an idea that represents we can get every number as big as we want. 0, and then every real number, there's an x that you could plug in to get there. So we get all possible non-negative outputs, and then the inputs can be any real number that we want, and that's it. So this is a solution to this problem where we use the graph, which is pretty acceptable. It's pretty good. If you can get a reliably accurate graph that captures kind of the overall tendency. We're not going to do anything too crazy. We're either just going to give you a graph, or we'll give you a mathematical expression where there are only a couple things going on, and then you just need enough sample points. And then you'll see what the range is from there. So the domain is maybe a better place to start. Actually, the domain is usually what it is the algebra for figuring out the domain is a little more straightforward. So we'll talk about that soon. So let's talk about well, for now we only have a few of our favorite functions to work with. Well, you figure out, well, one way of thinking about it that's usually good is you cross out all the regions that are not allowed, and then the domain is everything else. So once you get out of the bad numbers, everything else is the domain. So I have a few examples here. I want to make sure I don't accidentally do anything that's exactly the same. Let's start with something basic. So A, B, C, D. Maybe I'll have like 5 of these sort of variations on a theme. Square root of x, g of x can be square root of 2x plus 1. That's something you might think about a little bit. H of x is equal to, let's start with something kind of basic, and then maybe P of x is, actually I don't want to use just x all the time. You have to get lowercase t is also a very popular variable because t is often time. Let's do something else. Yeah, that's about right. Let's see. Oh, I want to make sure it's not too similar. Yeah, that's different enough. All right, so this one might be a little. The hint for this one is you'll probably want to factor that. And did I have a fourth one I wanted to do? Yeah, I think I'll do E before I do D. I think I wanted to do one that was slightly easier. All right, so for these problems, I'm only going to ask about the domain. A couple of these, you could actually find the range without too much trouble. Well, these are going to get a little bit weird. But A and B, you could, once you figure out the domain and then start graphing, that would be a pretty good follow-up question, is to figure out the range. Let's just let's just focus on the domain for now. So what inputs are not allowed? For now, we're going to interpret all of these as being functions which you input a real number and the output must also be a real number. There are other situations where if you allow the complex numbers to enter the picture, then things get more complicated and some outputs are suddenly okay. We'll sort of address that as we get to it, but if we treat these as functions of real numbers, from the real numbers to the real numbers, certain inputs are allowed and certain inputs are not. So for problem A, f of x is equal to the square root of x. That's the statement of the problem. We want to find the domain. But maybe let's just draw a real number line. Zero, the number 0 is actually okay. But negative numbers are not okay, and positive numbers are okay. So you can take a square root of any positive number, you can take a square root of 0. But the square root of a negative number, depending on your point of view, it's either some imaginary number or it's just strictly undefined. It's not a real number, so as a function from the reals to the reals, square root of -1 is just, it's not a real number. So if we define f to be a real valued function, the domain can only begin at 0, and then it keeps going to the right. Okay, so we'll get something similar for B, but what we have is a mathematical expression, and well, apparently for the square root function, 0 isn't a very important number. So what we want to know is the input 0, or is the input positive, or is the input, or is the inside of the square root, that is. So we can take the square root of 0 is happy face, square root of positive is happy face, square root of negative is frowny face. So let's look at 0 first. So question, when does 2x plus 1 equal to 0? That happens when 2x is equal to -1, so x is -1/2. So something really interesting is going to happen at x equals -1/2. And then maybe we take a couple of sample points. Well, we kind of know that 2x plus 1 is this nice sort of thing that varies kind of gradually. So you plug in, we go on our number line, we know that kind of everything should sort of fall on one side or the other, because the input of the square root, the 2x plus 1, we get exactly 0. So what happens is if we take g of -1/2, we get square root of, the whole point of this was we knew that was going to be really important. But then we plug in g of -1 is equal to square root of, so we have a -1 here, we end up getting square root of -1. So that's out of the picture. But if we plug in Well, here's a 0, we could check, positive 1. G of 0 is equal to square root of 0 plus 1, which is square root of 1, which is 1. And similarly, G of 1 is square root of minus 3, which is, so a picture of the domain looks like this. Bad things happen if we plug in x less than negative 1/2. Negative 1/2 is right on the borderline, but it's okay because square root of 0 is 0. X bigger than negative 1/2 is also okay. So domain we get starts at negative 1/2, goes all the way up to plus infinity. So that's what we're doing here. So it's like g of x is not quite the square root of x, it's the square root of this expression. So whatever's inside the square root, something funny happens at or nearby where x is where where that whole expression is equal to 0. So 2x plus 1 equals 0. That's when we're taking the square root of 0, and then we investigate nearby other places to do other good or bad things happen. It's if x is negative 1 or negative 2 or negative 3, we're taking square roots of negative numbers, and that's not good. But if x is 0, if x is 1, if x is 2, or if x is right on the borderline at x equals negative 1/2, you're getting square root of either 0 or a positive number, and that's totally fine. And that's letter B there. So for these two, if you wanted to find the range, you could plug in some x values. You'd use your calculator to get some decimals. For certain values of x, you would get a perfect square on the inside, and then you could find some nice one, but you could just use the calculator to get decimal places for whatever inputs you want, as long as they're inside the domain. If you plug in negative 2, you won't get a real number. Plug in negative 2, you won't get a real number. That's the idea. So I think I'll just erase the right-hand side. So last warning, or I guess you can always rewind. I'm doing a lot of erasing. I'm running pretty low on the spray here. Okay. But so we get to practice a little bit more of our interval notation here. We're gonna see something maybe we haven't seen in a while. Let's do C. So find the domain h of x is equal to 1 over x. Okay, so we're just taking the number 1 and we're trying to divide by x. Well, is there anything that can ever go wrong with that? We can divide by 3, we can divide by 4, 1/2, 1/3. We can divide by 2, we can divide 1 over 1 is fine. But like one of the first things that they're supposed to teach you on division day is, well, we can't really divide by 0, is it? So x, we can even divide by negative 2, and that's fine. It's we have rules for that, but 0 is just out of the question. All right, so what's the domain here? So kind of that the domain is, well, which sure, we can divide by just about any silly old number except for 0. Everything else is okay. So we get, well, we have this thing called interval notation. So we have this abstract idea of minus infinity. Anything bigger than minus infinity is okay, but we're not allowed to be 0, and this thing is called union. We include everything to the left of 0, and then we also include everything to the right of 0. So, you know, the United States of America is a union of 50 states. So if you're in Florida, you're in the union. If you're Alabama, you're in the union. If you're in Alaska, you're in the union, and so on. In the, you know, kind of literally same word, same origin. Just in mathematics, it's just you take everything to the left of 0, but not including 0. So it's not you don't include 0 in the left part, and then you don't include 0 in the right part. And that's the answer to C, is just that right there. So that's it. Let me write this, let me just write it down. I want to make some space again. Well, that's how you have to do it in the right order, because if you, as we'll see with part D, if you do it in the wrong order, you're just not saying what you mean to say, and things can get weird. So if there are like 3 or 4 unions, you just make sure you do them in increasing order. We'll talk about that later, but I want to do E. I'm going to jump back to D next. I wanted to do one slightly sort of an intermediate problem before we do the hardest one. I could even have the numerator be 1 plus s. Well, it's, you just look at the instructions and then the domain. The numerator, well, there's no problem. No matter what the numerator is, you can always have a 1 plus s. That's not the problem. We're not trying to take the square root of 1 plus s. It doesn't really affect the domain. The denominator is what's really important. It's what we're trying to divide by. Denominator equals 0 is bad. So that's bad, or just undefined. I guess bad is kind of a value judgment. Undefined. So if the denominator is 0, the expression, so if the denominator is 0, the entire expression is undefined. So this is, what do I call it? I call it Q of S is equal to all of that. All right, so 3s minus 1 is equal to 0 when 1 is equal to 3s, where s is equal to 1/3. So draw a picture, we're at positive 1/3, and we want to include everything else except for u. And we got minus infinity out here, so it's just minus infinity all the way up to positive 1/3 union with positive 1/3 all the way out to plus infinity. And that's it for that one. Part D is there's one sort of observation that you have to make, and then everything else will be fine. So rewind if you still needed that, and then pause. I wanted to jump back to D. So D, again, we're finding the domain P of t is equal to 1 over t squared minus 3t plus 2, which is 1 over, well, it's unclear, the way it's originally written, it's unclear what, how you make that denominator equal to 0, where the bad things happen, but if you factor it, suddenly it's a lot more clear. Denominator equals 0 when t equals 1 or t is equal to 2. Well, just draw in the number line and just don't do it, like, you can't do this, that would be bad. Or if this were a plus 2, and I don't know, if this one were a plus 1, then it was t equals minus 1. You have to make sure you get them in the right order, or else you're saying what you don't really mean to say. So let me show you a correct answer and an incorrect answer. So the correct answer is, okay, so yeah, I already wrote it. This one is wrong. I wrote these in the wrong order. I was so busy trying to teach you warning you about doing the wrong thing, and while I was talking, I actually did the wrong thing. So you can ask yourself what's wrong about this. Well, it'll be more clear what's wrong and what's right when I actually do it the right way. So, so 1 is when this part of the denominator is 0, then the whole denominator is therefore 0, and then again at 2. The right answer is well, here's the one that's really weird. We go from 2 to 1, we get the thing in the middle. That's, well, what does this one even mean is kind of an issue right there. So that's interval notation, except we have the bigger number listed first, which is completely incorrect. And then it's just, well, we avoid 1 starting from minus infinity. And then we go all the way up to 1. Then we avoid 1, so we start so we have an open interval starting at 1. We go all the way up to 2, but we avoid 2. And we go up to positive infinity. So we have all the numbers that are less than 1 are okay, and then all the numbers between 1 and 2 are okay. This is meaningless because the bigger number is first. What numbers are bigger than 2 and then simultaneously, how can be bigger than 2 and then less than 1 at the same time? Then this is kind of either nonsense or it's the empty set or something silly. Well, we don't use an interval notation for that. For interval notation, we put we want to say what we mean, which is the middle piece is bigger than 1 and less than 2. We're avoiding 2, and then we go from 2 to infinity, and we're avoiding 1, so minus infinity to 1. 1 to 2, 2 to infinity, and if it's all out of order, this one is nonsense, and these two are technically overlapping. So what does this one actually mean? Well, if I actually took this one, we'll pause it for the actual correct solution, but if you took the wrong answer and you were to actually do a picture of it, well, negative infinity all the way up to 2 is this. And then what if you also include 1 to infinity? Well, we've included the same stuff, but then we include it again if we go from 1 to infinity. If we did both of those, then we've already got everything, and it's just minus infinity to infinity, which is not what we actually wanted to do. What we wanted to do is we wanted to say, stay away from 1, stay away from 2, and then make sure you include the entire interval that's all 3 intervals that avoid those 3 points, and sort of split the real line into those 3 pieces. Then we're good. So if you write down the wrong thing, that's a picture of what you actually, that's what you're actually saying, whether you realize it or not. If you write down things in the wrong order and you just keep writing, just stop and make sure your number line has all the relevant points of interest, but in the correct order, and then you've got the structure, and then you can start filling in the specific information in between the gaps. So it's everything has to fall on a real number line that actually makes sense, and it goes from left to right, or where this is the smallest number of interest, so that's the next one, and then everything else happens in between. And then you can say what you mean to say, which is this thing right here. So roughly that's it. So the square root is kind of one example of the more math you do, the more famous functions there are that have their own domains of interest. And if you have a famous function, you just want to make sure whatever expression is on the inside, you want to be inside the domain of your famous function. In this case, you want 2x plus 1 to be non-negative, so that entire expression, sometimes it's 0, and then the other two, you can take sample points in the other intervals, and that was one type of problem. What else did we do? Yeah, we're dividing by something, so set the denominator equal to 0, and then you say, well, that's, if the denominator is 0, that's not in the domain. I think most of the problems are just only have you deal with one or two of these issues at a time. So more complicated combinations where you could run into both issues, I think that we're staying away from that for now. But just ask yourself what can possibly go wrong. You get a complete list of everything that you want to throw out, and then the function is well defined everywhere else, and wherever, all the places that are okay, that's your domain, and that's how you do it. Okay, so what else did I want to do here? So did I want to say more about range? Yeah, let's just take one quick look at range again. Yeah, just because this might be a little bit tricky. Yeah, let's do one that's slightly challenging. I think none of them are going to be any harder than this, but some of them might be borderline about the same. And this will be a good one to stop on. So let's do it. So one thing I suggest for approaching problems like this is maybe if it doesn't look too hard, maybe finding the domain algebraically is a really good place to start. So you can pause and think about that for a second. I'm going to take a sip of coffee. I'm encouraging you to give it a pause, pause it and think about it for a minute. So what's happening here? We don't divide by anything. The only function that we're bringing the square root function into the picture as a part of this larger function h. And we're taking the square root of x plus 1. And so the square root of a negative is not allowed, but so when does x plus 1 equal to 0? Well, that happens when x is minus 1. So that x equals minus 1 is going to be very important. So x equals minus 1 is going to be very important for the domain. And x equals minus 1 is okay if we plug in x equals 0. Square root, well, we're taking 2 minus the square root of 1. It's totally fine. So h of 0 so that's minus the square root. So sure, that's totally fine. 1 is totally fine. But h of -2, well, here we're going to run into trouble. So h of -2 equals 2 minus the square root of -2 plus 1. So equals 2 minus the square root of -1. Well, maybe h exists as a complex valued function, but if we only believe in real numbers, that's the end of the road. This is not h fails to be a real valued function when x is less than -1. So this tells us, so why do we start with the domain? Then that's a building block for figuring out how the picture is going to look. We know that we can do this. We're not going to just pick random numbers like -17 or -12. We know that -1 is really, really important because that's the very first number in the domain of h. So the outputs we put over here, we plug in -1, we get 2. So h of -1 is equal to 2. H of 0 is equal to, I'm going to pick nice numbers. It's equal to 2 minus 1. So let's see, if I plug in 3, I'll get a nice number here. So h of 3 is twice 2 minus the square root of 4. That is 0. So 2 minus 2 is 0. H of, I guess 8 is when something nice happens. So 2 minus square root of 9 equals -1. So 2 minus 3 is -1. When I plug in 8, and I'm kind of running out of space here. If I had to label my axes, so maybe make up my mind right now. I'll include it. H of 15 is 2 minus the square root of 16, which is 2 minus 4, which is -2. And I could have written a little bit smaller, but that's okay. What do we have? We have y values that go from, it only goes from -2 to 2. And x values, they start at -1, but they go all the way out to, like here's 10. I'll go a little bit farther so I can, here's 20, 15, 5. All right, so good enough. So when x is, here's -5, x is -1 would be right about here. We're up here at +2. When x is 0, we get 0, 1. When x is 3, it's running out of space here. But here's, so let's just label them. So -1, 2 is here. 0, 1 is there. 3, 0 is right about here. 30, 8, -1 is here. And then finally 15, -2 is down here. So it looks like if I were like really, really great artist, I could make it smoother, but computers can do it really. If you want it really, really good, you get a computer to do it. So we graphed, we found the domain, and now we just need the range. So you don't start from the top and go down. Just the interval notation is you go from smallest to greatest. So you start at for the range, you start at the bottom and you go up. Even if it looks like from left to right is like this, which would follow the y decreasing, but you want to, for the range, you just start at the bottom and you go up. So here we have y equals -infinity all the way up to and including y is equal to 2. And yeah, I did so much talking that it's easy to, when you explain things a lot, it's easy to forget what the original question was. But the original question says, hey, let's find the range. That was half of, well, the graph helped us find the range. The range is pretty tricky without a graph. But when you have a graph, it's a lot easier. It's one of the easiest ways to understand the range. And then what happens, it turns out that, yeah, so you can get the output y is equal to 2, and that's when x is equal to -1, but you can't go any farther than that. You shall not pass. Those are the range. Where did I say the domain? We computed it, but I don't think I wrote it down. So yeah, here's the step where I stop and I look at my work and I'm like, well, did I actually answer the question? I solved it, but I didn't actually write down my answer. I computed it and I said what it was out loud, but there it is. Double check, make sure I actually did it, and I turn that in, and there you go. All right, so that's domain and range. That more or less covers it. There's also functions in trigonometry. There's like all those buttons in your calculator, like sine, cosine, tangent, logarithm. Well, one day at a time. You can mess around with the graphs if you want to sort of start asking questions about that, but we're not there yet, and this is starting for now. The square root is a pretty good foundation for that. We'll look at the absolute value function as well, but that'll be a separate thing. I want to talk about piecewise functions, and the absolute value is a really good example of that. So we're going to stop this video right here. Hope that made sense. Make sure you look at this, go into the discussion and ask some questions. Even if you don't have your book yet, it's never too early to start learning about it. Try and maybe try to do some of the homework problems, even if you don't have the book yet. Just pick out the things that you think you understand. Give it a shot. Write some answers down. Put it aside. Come back to it later when you actually have the textbook. It'll doing as much as you can right now should help you stay a little bit more caught up for when all the books get here. It'll be a little bit crazy. We'll have some catch-up work to do. We might be playing catch-up for a while, but just do the best you can. But there you have it. Domain and range.